Hello everyone. In this video we will discuss the polygonal approximation of digital boundaries. The essence of this topic is, can we come up with a method by which I can represent a given boundary using a polygon which will be retaining the essence of the shape of the original boundary. And one of the most powerful methods of representing a boundary by a polygon is by using the minimum perimeter polygon or MPP. Minimum perimeter polygon or MPP. First, I will explain an intuitive approach to find the minimum perimeter polygon. In the first figure, I have a boundary of an arbitrary shape. In the second figure, a grid is superimposed over the first image, and we are finding a group of cells that encloses the boundary in the first image completely. Okay, so these are the cells. Okay, the one I have marked with a gray shade is a cell. Okay, now consider the original boundary in the second image as a rubber band and allow it to shrink. Then the rubber band will be constrained by the inner and outer walls of the cells. Okay, so this is the inner wall and this is the outer wall. And if you imagine the original boundary in this figure as a rubber band, and if you allow it to shrink, then you will get a shape of this kind. Ultimately, this shrinking produces a shape of a polygon of minimum perimeter. And you may note that in this figure, all the vertices of the minimum perimeter polygon coincide with corners of either the inner wall or the outer wall. Okay, so here it is coinciding with the inner wall, here it is coinciding with the outer walls. So by enclosing the original boundary by a wall of cells, we are essentially reducing the area inside the original boundary to an area that is inside the gray wall. That is, the area inside the gray wall is less than the area inside the original boundary. Now I have shown that reduced area with a dark gray shade in this image. If you traverse along the inner wall of this area, you can see that this boundary can be formed by some number of 4 connected straight line segments. And if you traverse this boundary in the counterclockwise direction, you will come across certain boundaries which may be convex or concave. Okay, so we are actually referring to the internal angles. So this will be a convex angle and this is a concave angle. The angle which is less than 180 is convex and which is greater than 180 is concave. And all the convex vertices are shown with a white dot and all the concave vertices are shown with a dark dot. Okay, so I'm doing the same to the all vertices along the boundary in this image. Now you see that all the dark dot and white dot are along the inner wall. And for every dark dot, we can find a point that is diagonally opposite to this point in the outer wall. So I can find a point corresponding to this point over here, and I can find a point corresponding to this point over here, and one over here, one over here, and one over here, and one over here, and over here, and so on. Okay, so in the last figure, instead of taking the dark dot on the inner wall, I am considering only the dark dot on the outer wall. And we see that the vertices of the minimum perimeter polygon coincide either with the convex vertices, that is the white dot, or the mirrors of the concave vertices, that is the black dot in the outer wall. A little observation will reveal that only the convex vertices of the inner wall and the concave vertices of the outer wall can be the vertices of the minimum perimeter polygon. Thus, our algorithm for finding the minimum perimeter polygon needs to focus the attention only on these vertices. Now we are going to develop an algorithm for finding the minimum perimeter polygon. As we saw in the previous discussion, we are representing a convex vertex with a white dot. I am giving it a symbol W, and every concave vertex is denoted by a black dot, and we are designating it with a symbol B. Now here we have some observations that we developed from the previous discussion. That is, the minimum perimeter polygon bounded by a simply connected cellular complex is not self-intersecting. That is, this boundary is not intersecting itself. That is, the boundary with a lighter gray shade is not intersecting itself. Now we have two important points that need to be noted. That is, every convex vertex of the MPP is a W vertex, but not every W vertex of the boundary is a vertex on the MPP. That is, this is my MPP, that is the boundary with the line segment is my MPP. And if you look at every convex vertex of this MPP, so this is a convex vertex, this is another convex vertex, this is another convex vertex, and this is another convex vertex. And all these convex vertices are at a W vertex, and you can also see that all W vertex are not part of the MPP. So this is a so this is an M, so here it is, here this is a W vertex, but so this is a W vertex, but this is not a part of the MPP. Okay. Similarly, every mirrored concave vertex of the MPP is a B vertex, but not every B vertex of the boundary is a vertex of the MPP. That means if you look at all the concave vertices, this is a concave vertex, this is a concave vertex, this is a concave vertex. So all the concave vertices are happening at a B vertex. And you can also see that not every B vertex of a boundary is a vertex of the MPP. So here you have two B vertices, but these are not the part of the MPP. Even though it coincides with the straight line, these are not considered as the part of the MPP, and we will see it later. Okay. And as the fourth point, all B vertices are on or outside the MPP, and all the W vertices are on or inside the MPP. So here I have a white vertex or a W vertex which is on the MPP, and this is a white vertex which is inside the MPP. Okay, so W vertices can be on or inside the MPP. Okay, similarly we have the B vertex which can be on the MPP or it can be outside the MPP. In this particular example, we do not have a B vertex which is outside the MPP. Now, as the last point, the uppermost leftmost vertex in a sequence of vertices contained in a cellular complex is always a W vertex. That is the uppermost leftmost, that is we are referring to this vertex, this will be always a W vertex. Okay, that is the uppermost leftmost vertex will be always a W vertex. So these are the certain observations that we need to keep in mind while we develop the algorithm for finding the minimum perimeter polygon. In the algorithm for finding the minimum perimeter polygon, we will have to use certain mathematical equations in order to understand the orientation of three different points. Okay, so here I have listed 3 points with coordinates x1, y1, x2, y2 and x3, y3, and the points are A, B and C. Using the determinant of a matrix, we can determine whether these points form a counterclockwise sequence or a clockwise sequence, or if the points are on the same line. So in order to do that, we will be forming a matrix A using the coordinates of the points A, B, C. The matrix A is formed with the values of the coordinates of A, B, C. So the first row is x1, y1, 1, then second one is x2, y2, 1 and x3, y3, 1. Once the matrix is formed, you will be calculating the determinant of that matrix. If the determinant of that matrix is a positive number, then the points A, B, C will be in a counterclockwise sequence, and if it is 0, then the points will be collinear, and if it is less than 0, the points will be forming a clockwise sequence. So this orientation will be there if the determinant is positive, and this orientation will be there if the determinant is negative, and this will be the orientation if the determinant is 0. For notational convenience, we will be writing sign of ABC instead of determinant of A, because this sign gives more sense, because we just need to understand whether determinant is positive, negative or 0 rather than its original value. Now we need to prepare the data for running this algorithm. For running this algorithm, We need to form a list whose rows are the coordinates of each vertex and an additional element denoting whether the vertex is W or B is also needed. And we have to arrange the vertices in the counterclockwise direction, and these are certain intermediate variables that we will be using while we run the algorithm. And we use two crawler points, that is WC and BC, and WC is a white crawler point and BC is a black crawler point, and these crawler points crawls along white and black vertices respectively, and V0 is the initial point or the initial vertex, and VL is the last MPP vertex found. So when you get all the VL points, that will be forming the MPP. Okay, and VK is the vertex that is currently being examined. Before we run the algorithm, we have to initially set WC and BC equal to the initial vertex V0. These are the main steps involved in the algorithm. That is, if Vk lies to the positive side of the line passing through VL, WC, that is, if sign of VL, WC, Vk is greater than 0. We have already defined this particular expression before, and if this quantity is greater than 0, then we have to set VL equal to WC and we have to reinitialize WC equal to BC equal to VL. Okay, and if VK lies on the negative side of the line passing through VL, WC or is collinear with it, that is, in other words, if sign of VL, WC, VK is less than or equal to 0, at the same time, Vk lies to the positive side of the line passing through VL, BC or is collinear with it. That is, in another words, VL, BC, Vk is greater than or equal to 0. Then we have to look at two conditions. That is, we have to set WC equal to Vk if Vk is a convex vertex, that is, if it is a white vertex, and we had to set BC equal to Vk if Vk is a concave vertex or a black vertex. And as the third condition, if Vk lies on the negative side of the line passing through VL, BC, in other words, if the sign of VL, BC, Vk is less than 0, then we had to set VL equal to BC and reinitialize WC equal to BC equal to VL. So we have to check each and every point in the list in each iteration, and finally the algorithm terminates when it reaches the first vertex again and thus has processed all the vertices in the polygon. Okay, and the VL vertices found by the algorithm are the vertices of the MPP. So these are the steps involved in the MPP algorithm.